Okay, so our next speaker is Frederic Galliano. We talk about investigating dust properties using a Bayesian approach of dust SCD model fitting. So Frederic, whenever you're ready, you can start.
Thank you. So I guess you can hear me well. Okay, yeah, thanks. So I will talk to you about a project that was prepared within the imaging collaboration. So it's a project about trying to understand dust in nearby galaxies with hierarchical Bayesian model. I will first talk to you a bit about the challenges of dust SCD fitting and why we are using a hierarchical Bayesian approach and also what it is. So that's going to be more the data science, aspect. Then I will briefly tell you about the result that we recently obtained applying this model on the M99 galaxies and try to get some constraints about dust evolution and then conclude. So first, since some of you, may not know exactly, how dust works, we already had a good introduction about dust yesterday, but I wanted to start from the basis. So basically, if you have a cluster of stars and you have a dusty cloud in front, you all know that, a fraction of the light will be not extincted by the dust, will go through the cloud. A fraction will be absorbed and a fraction will be scattered away. And actually, the fraction that has been absorbed will be at some point re-radiated thermally in the infrared. And so that's why when you look at a dusty cloud, in the visible wavelengths, you will see it essentially dark, while when you look at it at infrared wavelengths, you will essentially see it shining. And the fact is that those dust, at least in the interstellar medium, are so small particles that are, small solids that are basically everywhere. Radius goes from the size of large molecules to a bit below 0.1 micron in size. It's well mixed with the gas in the ISM. So it's essentially composed of about 2/3 of silicate and 1/3 of carbon grains, accounting for about 1% of the mass of the ISM. So those quantities can vary, and actually that's what we are interested in, actually, to try to understand how those properties, the size, the composition and the abundance vary within different environments. So either within a galaxy or even, among galaxies. Yes, so that's it. And because it's important to understand the star formation process and also galaxy evolution. But the key is that this process that you see here is actually wavelength dependent, and actually that's how we study it. So if you look at the spectral energy distribution of a typical galaxy, you see here it's the whole range from the UV to the radio. So you have the stellar emission that you see here. And as I should tell you before, a fraction of this radiation is absorbed by the dust. And you see that this absorption is wavelength dependent. It absorbs more in the UV than in the IR. And what has been absorbed is re-radiated thermally by the dust. And actually, that's this red curve that we are interested in studying, because it contains a lot of information about the composition, size distribution, and excitation of the grain. But the fact that there are also other processes that contaminate a bit this emission. So you have the gas. So you have gas lines that can contaminate some of the broadbands that we observe in photometry that we have to correct for. And we also have the free continuum that contributes in the millimeter wavelengths, the millimeter range emission, and the synchrotron continuum. And we typically study this spectral energy distribution of dust with data coming from the Spitzer satellite, Herschel, or more recently with the NICA-2 instruments at the IRAM 30-meter telescope. So first, how do we study that? So first, we need to know a bit about the physics of dust. So if we focus on the infrared wavelength range, so here I'm showing you the typical shape of the emission of a dust mixture in the ISM. One important aspect is to know that you have basically two processes, two types of components. You have the small grains that you see here that dominate the short wavelength emission, so in the IR and mid IR. that are out of equilibrium with the radiation field. So they fluctuate in temperature, and that's why they can emit at relatively short wavelengths. And then you have larger grains who are at thermal equilibrium with the radiation field, who all have more or less the same equilibrium temperature, and that have a spectrum that's similar to a gray body. And you have a transition between the out of equilibrium grains. And it has a consequence on the way we model this emission, because when you change the intensity of the radiation field, so this U parameter, which is the amount of light that a given grain is going to receive, that's going to depend on the environment. So when you change this parameter, you see that you have this effect. So here, the SED is normalized to the total power, so it's scaled to the same power. But you see that the emission from the small grain doesn't change much, while the emission from the large grain actually fits toward short wavelength, because the grains becomes actually hotter, and so on. So that's an important effect for the way we do it. And finally, in the literature, and also I will discuss it a bit, there is a common approximation that's called the modified blackbody approximation that essentially focuses on modeling the far infrared 2 millimeter range. And this approximation is just actually a Planck function times an emissivity law that is a power law of the wavelengths to a beta, which is a free parameter. So in a way, it's a very phenomenological, empirical way to try to understand how the slope of this emission at long wavelength varies depending on the physical conditions. So it would be simple if it was quite homogeneous, but the fact that when we look at observations of galaxies, even when we have angular resolution, we are always observing a mixing of physical conditions. And so there are different ways to account for that. I mean, but one common way in the literature is to adopt some phenomenological prescriptions. So here I'm showing you a typical observed SED in the ALMA of the galaxy, let's say. And the way we do it, and actually many other people do it, is to assume that there is a relation between the way the mass of the Earth is distributed and the starlight intensity that is exposed to, so the U parameter. And so it means that when we are actually fitting the SED of the dust mixture, we are fitting it with a distribution of radiation field intensities, and that's actually the shape of the radiation that constrains the range actually of these distributions. So the total looks like that. It's a way to compensate for our ignorance of the actual 3D geometries of the galaxy, because we can't really do an accurate subgrid relative transfer model for the galaxy. And from that, we can actually derive some parameters that are not very sensitive to the assumption that we put in. So we can derive some, I mean, the dust mass, also the average direct intensity, and also the mass fraction of the small grains, which actually control the strength of the aromatic tissue that you see in the pH that are very well observed by the DAOISM. And we can also account for stellar continuum and the sensitivity perspective. So that's the physical model that we usually use to try to interpret observations of galaxies. And the fact is that there are some methodological issues with trying to fit those SEDs. And the most well-known is the fact that you end up with a lot of noise-induced correlation between the parameters. So that's really something general for all these models. So here I'm trying to demonstrate it with the simplest case, so the modified blackbody. So here I'm showing you a simulation in the T beta parameter space. So you see we have a non-correlation between these two parameters for 100 sources. We have simulated for each one of these sources the corresponding SED. We have simulated the photometry and the noise. So if you were to observe real observation, you would start from this point, from the white arm. But the fact that if you don't take a lot of care in the way you do the fit, so for example, if you do simple least squared fit or even non-hierarchical Bayesian fit, you end up with invariant properties in the parameter space that look like that. So I mean, depending on the signal-to-noise ratio, the properties can vary, but the main feature is that you are going to induce a false correlation between those two parameters, which is not in the data. So it's an issue because actually we want to really understand if the parameters are linked or not, and what is the range. So one way to correct that is to have a method that is a bit more rigorous with the way the different sources of uncertainties are treated. And so that's the hierarchical Bayesian approach that we have implemented. And the main way to explain it is that the prior actually of the parameters of these sources is actually inferred from the data. And so it means that if we just start a Bayesian model from those points that you saw before, now the difference is that we are going to have one prior distribution of this parameter that you see here that is parameterized by hyperparameters. And we just infer the parameters from the data. So it means that when we let the Markov chain multi-parallel run that you see here, we accumulate statistics. At some point, the model is going to understand which part of the scatter is due to actually the real intrinsic scatter of the properties, and which one is simply due to the noise, because it treats all in a statistical way. So that's to give you an idea. And we can do that for all the parameters. So that's the code that we have developed in Spectral. So that starts from a collection of multi-wavelength maps, and we model, the probability distribution of the ACDs for all the pixels in our maps, even when we have quite a lot of upper limits. And we derive from that maps of the different parameters, the dust mass, parallelity, and so on. And another interesting feature of this code is that you can actually include other data that are not related to the dust model into the prior. So for example, here I'm showing you a simple example where we also have, it's also a simulation to demonstrate how it works, but here it's the distribution of the true values of the dust mass and the gas mass. The gas mass is not part of the dust model. So when we don't include the gas mass into the prior, so you see that at low column density, we have this kind of flattening movement. I mean, it's just because it's a typical, observational bias. But when, for the same data set, now we include the gas mass into the prior, then we can refine actually the acidity. Which means we can add some data that are not related to the dust, and with that, refine the field of the dust acidity. So it's really important. And just quickly, so I'm going to show you a few applications to Galaxy. So we have, our postdoc, Lara Pantoni, has recently published a paper on the Galaxy M99. So we are focusing a lot on the millimeter regime because it's really a domain that is crucial for dust mass estimate, because the dust mass is used to derive a lot of other properties. And the fact is that the millimeter opacity is actually the one that is the most probably known, and also presents a lot of variability. So we have used the data. Those are the observations at 1.2 and 2 millimeters in the galaxy. We have modeled the galaxy pixel by pixel, so spatially resolved, combining the stellar component, dust model, and also the frequency synchrotron. So you see the global LCD of the galaxy. We have also done additional modified black body fits. And so the first result that we have shown is that there is an evidence of large grain processing. So here I'm showing you the way the millimeter slope, so the data index varies as a function of the intensity of the ocean field. You see that you have a clear trend, and it's also even better correlated with the surface gas mass intensity. Which means that when you have denser ISM, you tend to have a flatter slope. And that's something, so in the diffuse regions, we already have the properties of the diffuse ISM here, which is the diffuse model, and with relatively negligible temperature variations. But in dense regions, we really have a steeper beta that is indicative of grain coagulation and mantle accretion that was demonstrated in this paper. Also, if you look at the shorter wavelength parts, the small grain, we also see some clear evidence of small grain processing. So here, if you look at the variation of the fraction of small grain, I mean, the grain that are emitting the hierarchical features, the AF, as a function of the starting opacity, again, you see that you have a clear decreasing trend. And it's also an evidence that is more well known, the fact that those small grains are very sensitive to the UV photons and are going to be destroyed in environments when you have a lot of those UV photons close to formation. So yes, it's you have a destruction of the small grains. And finally, also we have been able to look at the way the index of the synchrotron continuum varies as a function of the star formation rate, with also a clear decreasing trend. So that this one was also well known, but it's a good consistency check because those results are very sensitive to the residual that we get from the millimeter wavelength that we get to them. So this trend is actually an indication of the fact that far from suffering regions, you have sort of aging of the particular electrons that are related to the synchrotron emission. So just to summarize, I mean, I show you that this hierarchical Bayesian model is good at solving the formulation that we get from uncertainties, and that's it's really a not holistic approach. In terms of the results, so I showed you that we see some evident grain coagulation, foreground destruction, and the fact of the synchrotron correlating with the theta. And in terms of perspective, we are currently implementing the stellar evolution in the HerBIE code, and it will be the first public release, so by the overall with we are getting more statistics about these trends by adding more galaxies from the imaging sample. And we are also investigating the low metallicity aspect, so that's what Edin part is doing. And maybe just a short commercial break. So we have just opened postdoc fellowship for components. So if you are interested in the sector area, so we are going to hire 20 postdocs in physics, including astrophysics, so you can propose your project. Deadline July 15, and you must have spent more than 2 years outside of France in the last 2 years. And we are also organizing a conference about low metallicity ISM star formation 1 year from now, 2027 and 2026, in the final. Thank you.
Well, thank you very much, Frederic. That was a very nice, very complete talk. I'm sure people in the room have a lot of questions.
I missed. You said that when you include the gas properties, you have a better estimate of beta. Is that what I understood? Explain more.
So that was this point, I guess. Yeah. So the idea is that if you include gas mass into the prior, so the prior it's a function which is inferred from the data themselves. So if you, so it means that the model is going to also look for correlation between the gas mass and the dust mass, for example, and all the other parameters. And you see at 4 pixels that actually are quite noisy. That's why it's going to have more weight. So it's going to identify that, for example, this pixel looks at the same level as the other one, but it has a lower gas mass. So it means the prior is going to collect it and make it actually follow that.
So that means that the gas, the line in the continuum from the gas are very important. That's what it means.
Could be any other data. It could also be the star formation rate. It's not really.
It's not related to the physics.
It's a purely statistic. It's the fact that we have a large data set, and you naturally have correlation between these parameters in real life. When you have a low gas mass, you tend to have a low gas mass because at source or no, and so the model is going to find that by playing, with data.
Can't it be a bias?
I mean, it can be a bias depending on the shape of the prior that you achieve. If you have a very complex relation, if you have cutoffs, then you can do that, but you can always quantify the probability, so that's how it is.
Hi, thanks. Very, very interesting. At some point, maybe I missed it, but you mentioned also the influence of metallicity on dust properties. So are you also investigating the gas to dust ratio as a function of metallicity, for example?
But in other projects that we did in the past, in that so not only actually the effect of variation of the dust to gas ratio, but also the variation of the dust properties, the variation of small grains, and also of the optical properties of the grains at longer wavelength.
And up to which threshold of metallicity or whatever?
So the dust to gas ratio, we can typically in the nearby universe study it down to about 1/30th, 1/40th the lowest metallicity that we get. After, for the millimeter properties, we are a bit bad by the sensitivity of omega-2. So at the moment, we go down to metallicity of the SIT to about 1/5 below. It's very difficult to detect.
Thanks.
We have time for more questions, if anyone has any.
Thank you, Frederic. When I teach Bayesian statistics, I usually tell my students I have an a priori information, and then I have an update who allows me to improve your estimation. So I understand your prior is already based on some part of the data, but I didn't follow what is your update. What is the...
You're thinking the terminology of the hierarchical Bayesian. So if you do a non-hierarchical Bayesian of, for example, the example I showed below before, yes. Here, so if you assume that this model is non-hierarchical, it means your prior is the grid. It means for some reason you would have assumed that, and the posterior are the blue ellipses. And with the hierarchical Bayesian model, you have another layer of parameters. So you have hyperparameters that control the prior. So actually, this we still call it a prior, but it's not anymore a prior in Bayesian sense because it's information that we get at posteriori. So the difference is that now instead of having prior information on your parameters, you have prior information on your hyperparameters. And your hyperparameters are basically the mean, correlation, and correlation coefficients of this. You just have a different